This morning, I'd like to talk about the error in the interpolating polynomial. To figure out this error is kind of a long and tricky story, and we're going to begin with Raul's theorem. Suppose that you have a function that's differentiable on an interval from a to b, and the function values at the ends, at a and b, are both equal to 0. Raul's theorem says there's at least one number c in this interval so that f prime at c is 0. This is actually true for different values of the function than 0. As long as the function values at a and b are equal to each other, you could also draw this conclusion. The reason that this is true is not very difficult to see. Either the function is 0 all the way across the interval, or it isn't. If it is, then you have a value for the derivative of 0 at each point in AB, so the statement is certainly true. If the function is not identically equal to 0 on the interval, then somewhere it takes on a positive value or a negative value. In what follows, I'll look at the case where we have a positive value. The case where you have a negative value is similar. Since function f is differentiable, it's continuous. A continuous function on a closed interval attains a maximum and a minimum. And since we have a place where the function value is positive, the maximum value can't be 0. That means that the maximum must be attained at a point in the interior of the interval from a to b. Let c be a place where the function takes on a maximum value. You know from Calculus 1 that this tells you the derivative of f evaluated at c must be 0 then. Suppose f had 3 zeros. So we're looking at the graph of function f here, and suppose that it was 0 at x equal alpha, x equal beta, and x equal gamma. Looking on literally the one hand, since function f is 0 at alpha and beta, Raul's theorem says there must be a place between alpha and beta where the derivative of f is 0. Literally, on the other hand, somewhere between x equal beta and x equal gamma, there must be a place where f prime is 0. So we'll call these two places here C and here D. This tells me that I've got two places where f prime is 0. Now, I'm no longer thinking of the graph of y equal f of x. I'm thinking of y equal f prime of x, and we've just decided that there are two places where that value, the f prime value, comes up equal to 0. Therefore, by Raul's theorem, somewhere between C and D, there must be an x value, which we'll call E, so that the derivative not of f, but of f prime is 0. The derivative of f prime, of course, is the second derivative of f, so that tells me there must be a place where the second derivative of f is 0. You can continue this line of reasoning in an obvious way. What if f was 0 at 4 distinct x values, say a, b, c, and d? Raul's theorem tells me there must be numbers e between a and b, f between b and c, and g between c and d, where the derivative of f is 0. Apply Raul's theorem to f prime, though, And that tells me there must be a number h between E and F, and a number I between F and G, where the derivative of F is 0, so that the second derivative will be 0. Since the second derivative is 0 at two places, there must be a place between h and I so that the derivative of the second derivative is 0. So there must be a place where the third derivative is 0. So if you think about the general pattern here, if function f is 0 at a certain number of places, this means that there's a number c where the derivative of order 1 less than that certain number of places must be 0. Now, at first glance, this just appears to be incoherent rambling, but we have a place we're headed towards. Suppose we have a data set, as before, x0 f of x0 out to xn f of xn. None of the x numbers are repeated in the data set. We know already that there's exactly one polynomial of degree n or less that will interpolate this data. That is to say, p of xi equals f of xi for all indexes I equals 0 to n. I have a claim. If this function f has n plus 1 derivatives, if it's nice enough, then for any x value, the difference between f of x and p of x, this would be the error that I commit in approximating f of x with p of x. That error is exactly equal to the n plus first derivative of f evaluated at some number alpha divided by n plus 1 factorial multiplied by x minus x0 out to x minus xn. This is a very important fact. When we look at numerical integration methods, this is going to tell us the error in the methods. And since our differential equation methods are going to be built on top of the integration methods, this will also tell us about the error in the differential equations methods that we'll get to. So this fact is actually very important to us. Suppose that x was one of the x values out of your data set. Say it was x number I. Then f of x minus p of x would be f of xi minus whatever you get when you put xi into the interpolating polynomial, which is f of xi. So the difference would be 0. Over on the other side of the equation, if x was one of the xi's, then one of these factors is going to be 0. This means that this side of the equation is 0, and that side of the equation is 0. So the statement is true, even though it says nothing. This is also going to tell me how I'm going to get the error at points other than an interpolating point. This argument gets somewhat tricky. We already know all about what happens at the interpolating x values. So here's what we're going to do. We're going to select an x that's not one of those numbers. And I want to look at the difference between the function value and the interpolating polynomial at that x value. But I have to do this in a rather indirect way. We're going to cook up an auxiliary function, which I'll call phi. X at the moment is not the variable. X is some number that I've selected, and I want to look at the difference between f of x and p of x for that particular x value. So in most of what follows, x is going to be regarded as a constant. this function that I've cooked up is a function of some other variable, which I'm writing as lowercase script s. So I'm going to define phi of s to be f of s minus p of s. This fraction doesn't have s in it at all, so it's a constant. Also, since x is not one of the x0, x1, x2 out to xn numbers, none of these factors on the bottom is 0, so it's a perfectly well-behaved constant. F of s minus p of s minus this strange-looking thing, which is actually a constant, multiplied by s minus x0, s minus x1, out to s minus xn. And again, let me emphasize that for the phi function, it's the s that's the variable, not the x. And now the trickery will begin. What would happen if you evaluated phi at s equals xi, which is one of the x values out of your interpolating data set? Up front, you're going to have f of xi minus p of xi, which is 0, because p interpolates the data set. P at xi is f of xi. This is some constant. When I evaluate phi of s at s equal xi, these factors are going to be xi minus x0, xi minus x1, xi minus x2, out to xi minus xn. As you go down the list, sooner or later, you're going to hit a factor that's xi minus xi. You're going to hit a factor that's 0. So that makes this entire thing 0. So this phi function, we now know something about it. It has at least n plus 1 distinct real zeros. Now remember, x is being treated as though it's a constant. X is among the numbers that I could evaluate phi at by thinking of s as just being the x number. Phi of x is f of x minus p of x minus, this was my constant that I had before. When I substitute s equal x in, these factors turn into s minus x0 becomes x minus x0, so on and so forth, until s minus xn turns into x minus xn. These numbers and these numbers cancel each other out. If I take that special x number that I picked at the beginning and are holding constant, then it turns out that phi at that x is 0. On the other hand, x is not one of the x0, x1 out to xn numbers, so this tells me more than I knew before. This phi has at least n plus 2 distinct real zeros. Now, because of what we said before, 1 less than n plus 2 would be n plus 1. This tells me that there's some number alpha in the range of the x values from the data set, so that when I calculate the n plus first derivative of phi at that alpha, I get 0 for an answer. On the other hand, I have a formula for phi. The n plus first derivative, phi evaluated at s, is the n plus first derivative of f at s minus the n plus first derivative of p at s minus this constant times the n plus first derivative of s minus x0 out to s minus xn. It's worth mentioning in this product here If I started calculating with index 1, I'd have s minus x1, s minus x2, out to s minus xn. That would be n factors, but then you also have the s minus x0. So that's the n plus first factor. I'm taking the n plus first derivative of a polynomial in terms of s that's of degree exactly n plus 1. In the preceding formula, you had the n plus first derivative of p evaluated some s, but that's 0. P is a polynomial of degree no more than n, and I'm taking a derivative of order more than the degree of the polynomial, so I get 0 for an answer for that piece. There's a constant factor which at this moment is not of interest to me, but what about the n plus first derivative of these n plus 1 factors of s minus xi? If you were to multiply this out, the lead term would be s raised to the n plus 1 power, and then you'd have lower order terms. Those lower order terms don't worry me in the least, because when I take the n plus first derivative of them, I'll get 0. It's only the s to the n plus 1 that's going to contribute anything. So even though I'm not going to prove what I'm about to say, I want to at least convince you of it. The third derivative of s to the third power is the second derivative of 3s squared. This is 3 times 2 times the derivative of s with respect to s, which is 3 times 2 times 1, which everyone will recognize as 3 factorial. Not to belabor the point, but if you work out what the fifth derivative with respect to s of s to the 5 power is, it's the same kind of calculation, and in the end, you end up with 5 times 4 times 3 times 2 times 1, which is 5 factorial. If I take a derivative with respect to s of a certain order of s raised to that same power, what I'm going to get at the end will be a constant. It will be the original order of the derivative factorial. So I'm going to go back and think about evaluating the formula on page 14 at s equals alpha. That's the special place where the n plus first derivative of phi was 0, which we know exists because of Raul's theorem of all things. Now, you'll notice that the n plus first derivative of p of x is not in the formula anymore. That's because we figured out no matter what, that's going to come up 0, so there's no need to write it down anymore. Using the fact that the n plus first derivative of phi at alpha is 0, we can finally get close to our answer. From the preceding formula, which said that a certain difference was equal to 0, it follows that this quantity and this quantity must be the same. We're almost done. Multiply both sides by x minus x0 through x minus xn. Divide both sides by n plus 1 factorial, and we find out that the difference between the function value and the interpolating polynomial is what we claimed it was going to be. So as I said before, this will be very useful for us when we're doing numerical integration and differential equation methods. And one last thing. If I give you n plus 1 distinct x values, call them x0 through xn, and I give you any polynomial of degree no more than n, I claim that it's always possible to write that polynomial in the following strange format: a constant plus another constant times x minus x0 plus another constant times x minus x0, x minus x1, all the way out to some constant an times products of x minus x values out of the data set, except you only have x minus x0 out to x minus x number n minus 1. If you started counting at 1, you would say that you had n minus 1 factors, and then including that, you have n factors. So we want the polynomial to be of degree no more than n. I don't want to include the x minus x n in this. The easiest thing to do is to make up an example. And this should have been x2. It doesn't affect the calculation though. I'm going to have x values 1, 2, and 5. My polynomial is 5x squared plus 6x plus 1. I picked these numbers at random out of thin air because I want to show you that you can write this polynomial as a0 plus a1 times x minus 1 plus a2 times x minus 1 times x minus 2. This is a polynomial of degree 2 or less. There is exactly one polynomial that will interpolate this data. One of them, obviously, is 5x squared plus 6x plus 1. If it turns out that I can make another polynomial that produces the same values for my function at 1, 2, and 3, then the two polynomials will have to be the same because of the uniqueness of the interpolating polynomial. So on the one hand, when I look at x equal 1, in my original version of my polynomial, 5 times 1 squared plus 6 times 1 plus 1 is 12. On the other hand, if I have a polynomial in this format and I evaluate it at x equal 1, this term will be 0, and so will that one. And that says that a0 has to be 12. Look at my next x value, x equals 2. In the original form for the polynomial, if you plug 2 in for the x, you get 33. On the other hand, if you plug 2 into this other form, we already figured out the 12, a1 times 2 minus 1, a2 times 2 minus 1 times 2 minus 2, this is 0. This simplifies down to 12 plus a1, and I want that to be the same function value that I got out of the original polynomial. And after doing a little bit of algebra, it turns out that a1 needs to be 21. Finally, I want the function value in my original polynomial and the function value in this strange-looking polynomial to be the same when x is 5. Evaluate the original thing at 5. The value is 156. Evaluate the odd-looking strange new form at x equal 5, and you conclude, after doing some algebra, that a3 must be 5. So the polynomial 12 plus 21 times x minus 1 plus 5 times x minus 1, x minus 2, produces the same function values as 5x squared plus 6x plus 1 at the 3x values indicated. There is only one polynomial of degree no more than 2 that does that. So even though it doesn't look like it, this and this are the same thing. They're the same polynomial. if I've done all my work correctly, you could sit down and simplify all this stuff, and when the dust finally settled, you would get 5x squared plus 6x plus 1. Notice that the highest degree term has a coefficient of 5, and we have a 5 here, but the other coefficients don't have to match up. This is 21x minus 1, and this is 6x. The reason they're not the same, you're going to get some first degree terms contributing out of the last one here. Also, the constant term here is 12. The constant term here is 1. That's because you're going to get a constant term contribution from here and a constant term contribution from the other one. So don't make the mistake of thinking that this number, and this number have to be that number, and that number. Usually it's not true, although it will be true for the highest degree term. This strange factored up version of the interpolating polynomial is called the Newton form, and our next topic is going to be developing efficient methods to calculate the values of the Newton form of the interpolating polynomial. That's all I wanted to talk about today. I hope everyone's having a good day. We'll talk again soon.